Section P5 is going to continue our discussion of polynomials. We're going to kind of go in reverse order of what we did in the previous section. In the previous section, we were sort of distributing everything out and minimizing everything by eliminating all of the operations that we could. You know, if there's an addition that could be done, we did it. If there was a multiplication that could be done, we did it, right? This section very much is in reverse. It's factoring, which means you're breaking things down instead of combining them together. So to start with, if a polynomial cannot be factored, it has a name. We call it prime, and that's what we would have called a number, right? We call the number 2 prime because it doesn't break down into anything different than itself in 1. So 2 is a prime number. So the same thing is true for a polynomial. If it cannot be factored down any simpler, we call it prime. That's the better term. There's another phrase as well. It's called irreducible over the integers. Who likes prime better? Me too. Yeah, it's just way simpler, and it has this nice harkening back to how we describe our numbers, and we're dealing with factoring as well. The simplest type of factoring are greatest common factors. So greatest common factors means that you have 2 or more terms. Okay, so we've got a polynomial that's either a binomial or a trinomial or something bigger. And we ask ourselves, does everything that I've got here in this polynomial have anything in common? And this one does. We start by looking at the coefficients. The coefficients are 12 and 18. And we ask ourselves, what is the biggest number that will divide 12 and 18? And we do want the biggest one. 6. 6 is the largest number that will divide 12 and 18. And let me show you in a moment here what happens if you accidentally don't pick the biggest one, so that you can see how you'll know very quickly that something bigger worked. But let me just go with the 6 for the moment. Then you look at the exponents, the variables with the exponents. I have x squared, which means there's x times x, and x cubed, which means x times x times x. So how many x's do they have in common? 2. Each of them have at least 2 x's in it, which means x squared is what they have in common. Okay, so if I were simply asked what's the greatest common factor, we would be done. The answer would be 6x squared. If we're asked to actually factor using the greatest common factor, what that means is that we will continue to write what happens when I pull or divide or factor out that greatest common factor. So 6x squared comes out of 12x squared. So when I take the 12 and I divide by 6, I'm left with 2. And when I take the x squared and I divide by x squared, I'm actually left with 1. I mean, right? It's division. But 2 divided by, not multiplied, 2 multiplied by 1 is just 1, or is just 2. It doesn't change it. All right? So I've pulled the x squared out completely. After that, I have minus the 18x cubed. So it's still negative because I didn't take out a negative. And I do the same thing. 18 divided by 6 would be 3. But if I had x cubed and I divided by x squared, or I pulled out x squared, how much do I have left? I still have an x left. And this would be the factored form for this. Now, sometimes numbers are not as nice as 12 and 18. I think that's a fairly nice set of numbers. It's not something that's sort of large enough that you might not catch it. But I'd like to show you, just using this example, what would happen if you didn't catch it as the largest value. So let's say, for instance, you looked at 12 and you looked at the 18 and you recognized that they both divided by 3 or 2. Let's go with 2 because I think 2 might be sort of like the trigger number because we like numbers that are even. And we say, I know it divides. It's even, it's even. It's evens everywhere, right? So let's say you looked at this and you said, yep, there's a 2x squared in it. You didn't catch that it was a 6. You thought it was a 2. And you went through the problem and you said, okay, 12 divided by 2, that's 6. Now I have 6 left there. The x squareds cancel. That's totally fine, or divide out. And then I have 18 divided by 2, so that's a 9, x, right? So this is where I am. So it's a good idea when you get to the end of the problem, whether it's here with the 2 minus 3x, or whether it's here if you would have accidentally gotten the 6 minus 9x, and ask yourself, does what's left in parentheses have anything in common? And this one does, right? So at that point, you have a couple of options. You can go back to the starting board and say, okay, 2 wasn't big enough because I still have something in common inside, and you can look for something bigger. Or at that point, you can look at it and say, hey, look, 6 and 9 still have something in common, and I know what it is. It's a 3, right? So you could pull the 3 out at this point. So you could say, okay, well, I already have the 2x squared, but I need to pull out a 3 still here, and when I divide the 6 by 3, I get 2, and I divide the 9 by 3, I get 3x, and then you can multiply these together to give you 6x squared. So you can either go back to the beginning and try for something larger, or you can continue working with the smaller pieces and then take the results and multiply them. You'll still get to the same point as long as you're asking yourselves those appropriate questions along the way. So greatest common factors is the most widely used initial starting place. You should start there for every set of problems. Now, not every set of problems will have factors in common at the beginning. The next one that we're going to look at are 3 different special formulas for factoring. And they each have names. So this first one is called the difference of squares. I'm going to leave a space and I'm just going to write it out to the side. And of course, I mentioned that just a little bit ago as being related to the conjugate, difference of squares. Difference, because it's subtraction. Squares, because they're both squared. The second one is also a difference, so it's the difference. But what do you notice about those two terms? Yep. This is the difference of cubes, because both terms are cubed. And the last one is not a difference at all. It's a sum of cubes. So it would be a natural question for you to see this and say, well, what about sum of squares? There's sum of cubes, and there's difference of squares and difference of cubes. Where's the sum of squares? Sums of squares don't factor. They're prime. So that's why you don't see them show up here. They are prime over the integers. We actually will see them in section P.7, but we won't be using the real number system when we get there and we notice it. So they're coming, they're just not happening here, all right? So for working with integers and working with specifically real numbers, these are the 3 special formulas that do exist over the integers. So a difference of squares actually factors into a plus b and a minus b. And that's why it's related to the conjugate. 2 terms, they match, except for the interior sign. One's positive, one's negative. That's the simplest form formula here. The other 2 actually have a component of it that will mirror the original pattern that you see. For example, this looks like a cubed minus b cubed, so it looks like it's got a subtraction sign. So we're going to end up with a binomial that says a minus b. It looks just like it, but without the cubes, because that's part of the factoring piece. The sum of cubes is going to have an a plus b. All right? The other piece is actually a trinomial. And I'm going to try and, I'll write it all out, of course, but I'm going to try to sort of think through with you how I remember them. So what I remember is that I need to get something cubed. And so in order to do that, this would have to be an a squared, because I'm going to have an a squared times an a to give me a cubed. And I'm going to have the same thing here at the end, a b squared times a b to give me a b cubed. Okay, so those components must be there. In the middle, I need the opposite sign of whatever I had. So on this one, it's positive. And I need the 2 values multiplied, a, b. And if I follow that pattern, it works as well for thinking about the other one. I have an a squared, and I have a b squared. It is plus b squared. I have the opposite sign, which on the second one is subtraction, and then I have the a and the b multiplied. That's the pattern. Okay, so somebody asked me about something the other day, not in this class, so let me just kind of make mention. When we get to a test, yes, you need to know these. Like, they're not going to be provided for you. So whatever that means for you in terms of memorizing, if you don't already have these in the back of your mind stored away somewhere, you're going to need to memorize them at some point. So start working on thinking about that as you're doing the homework would be a good plan. All right, so we're going to use these now to factor things that are in that form. So the first one is actually in the form of squares. But it will really help you if you actually change them to be what's being squared. For example, it's not really the 9t that's being squared. T is being squared, but there's actually a 3 here, right? 3 squared is 9. So it's the 3t that's actually squared here. And it's not 16 that's squared, it's actually a 4 squared because I have a 16. So the pieces that identify back to our formulas over here on this previous page are not 9t and 16. They're 3t and 4. So making that identification is the first step. After we've done that, those values, the 3t and the 4, are exactly what go into the parentheses. I have 3t, and I have 4, and I have 3t, and I have 4, and the difference of squares formula says one's positive, one's negative. And I'm done. Okay? Now in number 3, you might look at that and say to yourself, well, I don't really necessarily see things that are squared nicely or cubed nicely. You with me? It's true. And the reason that that's happening is because I mentioned earlier over here when we did this, that the first thing that we really should do when we're working with a problem, which I didn't do already on the one I did because I recognized what was happening, is look to see if they have anything in common that I can pull out. So over here, the 9t squared and the 16 actually didn't have that. But my 8x to the 4th and my 27xy cubed do. What do they have in common? Well, the 8 and the 27 don't have anything. But what about the variables? They both have an x in them. So before I get too far down this line, I need to pull an x out. So if I pull an x out of x to the 4th, I end up with x cubed. And if I pull an x out of the 27xy cubed, I have 27y cubed. So then, I need to do the same thing I did before. I need to identify what's actually being cubed. Well, it's not an 8. What cubed will equal 8? 2. There is a 2x being cubed here because there's a 2 cubed to give me 8 and there's x cubed to give me x cubed. And then on the second piece, I'll put this in brackets just to differentiate it from the x at the beginning. On the second piece, what number cubed would give me 27? 3. So it is a 3y that's being cubed to give me 27y cubed in total. And then applying the basic formula from the previous page to this, there's still an x out in front. Okay, don't lose it along the way. But I have a binomial and I have a trinomial. The binomial will look just like the values that I have without the cubes. So there'll be 2x minus 3y. And the sign's the same as well, matching signs. The other pieces get squared. So 2 squared is 4, so this is 4x squared. 3 squared is 9, so this is 9y squared at the end. The signs on both of those are always positive. The sign in the middle is going to be the opposite of the sign I already have. So I have a negative here, I have a negative here between the 2x and the 3y, so I need a positive in the middle here for my term. And then I need the 2x and the 3y multiplied. That's what it is. So what does that give me on this one? Yeah, 6xy. And that would be my factored form. So we will pause right there today. We will pick up with number 4 next time and then move into section P.5. So you can start this assignment if you wish. You do not need to finish it. We are not finished with the material for the lecture portion, all right? So this one, P5, I said it all wrong. This one, P5, will not be due until Tuesday next week.